Okay, so right. So on Slack, we'll be in this new section here. So everybody should join the data pipeline Slack. And you should be in the O2 data pipelines directory of the Git repo. Minimize that. So a lot of the new HPCs that are coming online these days are hybrid systems. So they have CPU, GPU, both of those on the same node. Many of them are 1 or 2 CPUs with 4 to 8 GPUs. Theta GPU has 2 CPUs and 8 GPUs. As you saw in the data science or in the data distributed deep learning section, typically it's easiest to run on those systems with multiple ranks per node, where you decide on the number of ranks, the MPI ranks, based on how many GPUs you have per node. So I'm going to talk a little bit about while your, TensorFlow and PyTorch, while they've been optimized to use the GPU for all the machine learning, math operations. So now you've got a whole CPU sitting there doing nothing while all the math is being done on the GPU. What should you do with it? Well, you should use it for preparing your data for the training loop, which is being operated on the GPU. So the data set we're going to use here for this example is the Imagenet data set. So this is what they use for the Imagenet challenge. It's a data set with over 1 million total images with about 1,000 different classes. These are JPEGs stored that, every image is stored as a JPEG. Each image has an XML file that goes with it that annotates the image. So it will provide a bounding box for the class object and the class ID. And so we're going to use those as examples here. I'm going to focus on the TensorFlow dataset abstraction because it just seems that the TensorFlow dataset API is a little bit more well-defined and versatile than the PyTorch. I do have a similar PyTorch example in here that you can take a look at, but we'll focus on the TensorFlow dataset API for this workshop. Let's see, so these, yep, that goes there. So I just wanted to go over some of the basic pieces that you'll see in the example. And so if you click here, it'll take you to the example that we're going to be looking at. And this is just a piece of Python code that you can run on the command line. But we'll go through a little bit of it. So I have this function called build dataset from file list. The way we're going to loop over this data is I have a text file with a list of all the JPEGs. So here we're just opening that file, we're looping over that list and putting it into a Python list. Then the TensorFlow dataset API has this nice from tensor slices. So we take that Python list object, and this converts that list of strings into TensorFlow tensor of strings. Next, we're going to tell TensorFlow that we intend to use MPI. So we're going to run parallel distributed training, and we can use Horovod to decide how, or to tell TensorFlow how it's going to shard up this data, as they say. And shard seems to be a common term between TensorFlow and PyTorch. So if you search for that in their documentation, you'll find similar functionality. And this is just grabbing the total number of ranks, MPI ranks, and this particular MPI rank. So it's saying how many shards are there and which shard am I? And that way it can pick out the data set that it's going to process in this local MPI process. The next thing we're going to do, and you can see I'm just overriding, I'm using the same file list variable each time. The next thing we're going to do is we're going to shuffle this file list. Okay, so we shuffle the whole thing. We're going to use, there's a config file that's just a JSON file that defines the shuffle size of the buffer. It's important that this buffer be large enough that it captures multiple classes. So let's say my file list was 100 files and it was organized in groups of 10 files with one with each class. If my shuffle buffer was only a size of 10, it's going to bring in the first 10 images and shuffle them, but since they're all the same class, it doesn't really matter. When you train, you want to have a randomized set with many different classes in the same training batch, so it's important that this shuffle size be big enough. And then there's this reshuffle each iteration, which just says after the end of the epoch, shuffle them anew so that you don't have the same ordered list for every epoch. Now TensorFlow has this ability to run custom mapping functions on your data set. So in this case here, I have my shuffled, sharded file list, and I'm going to map it with this load image label, and BB is bounding box. This is a custom Python function that I wrote for the Imagenet, and it's in the example file. You can have a look at it. But it's essentially going to open the image. It's going to also open the corresponding XML file. It's going to extract the bounding box information on the class. It's going to extract the class information from the XML file. Then it's going to use that bounding box to chop up the image so that it's a single class per image, and it's going to associate that label with that new image. And the key here is this number of parallel calls. This allows TensorFlow, or you're telling TensorFlow that you can run this mapping operation on elements of the file list independent of one another and some number of times in parallel. And then TensorFlow has this nice auto tune where it will try to set this dynamically based on the system and the resources that are being utilized. So far, I haven't seen any problem in making this choice with running multiple ranks per node. This is what I would recommend you keep it as. But if you wanted to, you could set this to an actual number if you wanted to hard code this somehow, or force it to some number of parallel threads. So this is where some of the data parallelization on the CPU is happening, right? So we're going to run this on the CPU side to build up our training batches, and we're going to tell it to run this mapping call in parallel. So next, this outputs a data set, but this data set has, in some cases, most of the images are one class, one image. So this image is going to have a bounding box that's approximately as big as this dog, and it's going to have a label that corresponds to the dog. This image is going to have a bounding box that's almost the entire image and has the class of a turtle. There are a few images in the data set, just to make it complicated, that have multiple classes in them, but they're all the same class object. So it might be 3 turtles in the same image. So by chopping up these into individual images, I'm just simplifying the problem a little bit in this case, because I didn't want to have a bounding box YOLO style example. So the point is that the return from this is going to have, some of the outputs have multiple images and some don't. So we need to unbatch those images. So we're going to flatten our vector essentially in the first dimension. And then we're going to rebatch based on the batch size that we set in our config file from JSON, from a JSON dictionary. So this just is a configuration that tells us how many the batch size that we're going to use. Now we can call this prefetch on the data set. So this tells TensorFlow that instead of waiting for the user to say, here, I'm ready for my next batch, this tells TensorFlow that it can go ahead and start building batches ahead of time. And the buffer size decides how many batches to preload. And again, it will accept this auto-tune variable, which I so far have had no trouble with. So with that, we are done building our data set, and it will operate and do these things in parallel. And then we can do something like this in our training loop. Maybe this is the inner training loop, right? We have a loop for epoch, but then we have our inner training loop where we iterate over the data set, and the data set returns the inputs, the input vectors, and the labels, right? And then we run our model on our inputs, get the prediction, calculate the loss function between the prediction and the labels, and so on and so forth. Okay? So I have this example down in the TensorFlow dataset API, and we're going to run through that. So I'm just going to come over here to my terminal. You guys can still see my terminal when I switch desktops. And is it legible? I have to make it a little bigger. Let's go over here. Someone say yes if you can see my screen still. Yes. And you're looking at a terminal is what you should be looking at. Anybody?
No, you're back on.
Looks good.
Okay. Everybody's asleep maybe. Okay. So what I'm going to run is qsub, and I'm on Theta GPU, so I'm going to run the Theta GPU script. And actually, I think I need to do this. Okay, so that's going to submit a job. I'm just going to cat that script real quick. You can see it's going to use one node. For the moment, I'm just doing one process per node, just because we don't need to worry about the MPI parallelism for this example here. And so I'm just going to run qstat and see what's going on, make sure my job is actually running. There we go. See a few other people running, good. Feel free to run along with me. There's also a Theta submit script. So you can be on Theta and run this example as well. Now, the script is set up to dump everything into the log directory here. So if you just do an ls, my job has my directory has old jobs that I've run, but if I find my job ID number, I can do logdir job ID number, and check the error and the output. Make sure everything's looking okay. So I have this example using the Python logging module, which strangely outputs to standard error. So if you want to find the status information, you can go to standard error, and then what you'll see are printouts that show you for every batch number that we run, you can get the input shape, the label shape, and then I also print out the label vector just so you can see these are class labels from 0 to 1,000, as they should be. They are randomized, so the shuffle is working. And I run that for, I don't know, 5 times, I think, maybe 10. And then I also provide the number of images read per second, okay? And I have examples in this directory. I have a serial example, and we didn't run the serial, we just ran the standard example. The serial example uses these configuration options for TensorFlow, this threading options for setting the inter and intra parallel operations, and it fixes them to 1. So that's what the serial is doing differently, whereas the script without the underscore serial allows you to set these via the command line, and otherwise defaults to the default from TensorFlow, which I believe is the number of cores, but we can check. So, Tyler. So you can see in my submit script, I set the number of OpenMP threads to 64, and I pass those as the settings for the interopt and intraopt. And you can play with these a little bit, and depending on your workflow and what you're doing for your data pipeline, it's useful to play with these, change these to different numbers, have a go on a node and see how your performance, your training throughput changes. And I include these images from the TensorFlow profiler, which we'll talk about tomorrow, to give you an idea. So if you run that example, I was running this interactively with this command, but otherwise you can also use the submit scripts. If you run the serial example, in this case, what I saw was this blue at the top represents one training or one step where it's building a batch. So you call the iterator to get one batch, and this is how long it took to return that batch and build it. And you can see in the serial mode, this was taking about 10 seconds. This was on, no, I didn't write that down. I think this was on, this was on theta. Yeah, because I'm using the module load. So this was on theta, not theta GPU. And then when I moved to not using the serial, and then I also set the inter and intra-op settings to 64, that shrinks from 10 seconds to about 1 second. Oops, don't click on that. So you can see in this example here, there's literally one compute thread running that's running these read file calls, right? So this is reading the JPEG, right? You can see the green. File IO is really bad for performance, especially because these are small files. These JPEGs are on the scale of 10 to 100 kilobytes. And on shared file systems, this can be lead to very poor performance. And you can see that you're actually, when you're hitting the shared file system so quickly for all these small files, you may end up in a queue where someone else has asked for information from the shared file system, and you're just going to have to wait until it gets to you. And so you can see some of these read files take longer. Some of them are quite short, like here in these here, you can see there were some calls that were quite fast. So this is a problem for performance. It slows you down. So if you increase the number of ranks, this is one way to help. And I'm using this very brute force-like, right? I mean, ideally what you would really do is you would pre-process all of these JPEGs into bigger chunks that represent your batches, and that would be much better performant on the file system. So I don't want to give you the impression this is the best way to build a pipeline from this kind of data. I just wanted to use it as a way to show you how the parallelism helps you. So if I go to using these 64 threads, you can now see I have many of these threads running, and this goes all the way down to 64 if you counted them all up. And we've shrunk our build time for a batch by a factor of 10. And you can see that many of these threads do the work that they need to do very quickly. I think the batch size I was using was 128. So in principle, 64 threads only need to open and read 2 files each. And so what you see is there's a lot of white space now, which means most of the threads have finished their work and idle. And actually, if you scroll down this list, what you would see, because you see the read files here, and this is where it's calling the custom function where it's reading the XML file, which is another file IO issue. And what you see is those reads are the thing that end up, sometimes they take long because lots of reading from the same folders and the same files is an IO bottleneck. So again, ideally, I would go through and I would dump all these JPEGs into, you know, TensorFlow friendly data formats with many images in the same file, and so on and so forth. But for the sake of showing that this parallelism helps you shrink this batch build time, okay? And we'll go over the profiling tomorrow so you can get a better idea of what these look like. Are there any questions? Maybe people are, nope, okay. Thanks, Kyle, for the fun facts. So you can also run this on theta. I'm trying to think, was there one other thing I wanted to say? Right, so the other thing that you'll see, especially when you use this prefetch, a lot of the things like TensorFlow and Torch will take time to build the first, before you run the first, or when you start the first execution of your model, they will compile during runtime your model into source code or into machine code. And that takes time. And it takes longer than the typical bunch or the typical training step. And the prefetch will actually, when you run these profilers, excuse me, you will see during that period of time, the CPU will already be building your input batches for you. So that is also something you would see, but I zoomed in on a later loop just so. So you guys feel free to run those examples. Because I don't want to. I can also take a look at the, can dig here a little deeper for a moment. Like I said, I didn't expect this session to take as long as the first. So we can also go back to those. So here's the function that I went through with the build data sets from the file list, where we get the we get the file list from the text file that's input. And maybe I should show, this is our input configuration file. So this is just specifying things like the data set, shuffle buffer. You can see I set to 200,000, which is about 1/5 of the total data set. The reshuffle, the number of parallel readers, and the data files. I also set the crop image size. So every time I use those bounding boxes to crop the image around the turtle or the dog, we need a stable input for our model. So you need a fixed image size. And so TensorFlow provides a tool for cropping and resizing images. And so you just provide it the shape you want output, and it will renormalize the image for you. So here you can see the loop. So we get our data set here. And in this case, I actually get an explicit iterator for the training data set because of the profiling, which we'll talk about tomorrow. And then I call the next to grab the data set input and labels, whereas this would normally just be 4 inputs and labels in the training data set. Okay.
I have a question.
Yeah.
If you do not have any data pre-processing, do you still recommend using this API?
So again, if you don't have
Data pre-processing. So I've had data where all I really need to do is like load it and use Horvath to split it over the GPUs. Would I still
yeah,
save time by using this API?
so I guess I would say it depends on how the data is stored. If you can fit everything into memory, that's one thing. The other reason I wanted to use this example is because it's really useful for people that need to load their data dynamically.
Mm-hmm.
Right? There are many cases where your data set is so big where you just can't shove it all into RAM and hope for the best. So I wanted to show that pipeline where you can, you know, um, have that iterating over in a smart way.
Yeah.
Now, if you just had a big monolithic file, I guess there's no benefit. Um, Although, that being said, I mean, you are going to want to randomize your data sets, even if you can fit it all into memory.
Mm-hmm.
And you um, can use right, I mean, you have the prefetch, you have the multiple, the parallel worker aspect, um, which I guess if it's all in memory, you don't need per se. But you do have the shuffling and the prefetch that you could in principle still use if you wanted to.
Yeah, that makes
And
sense.
you have to put it into a TensorFlow tensor at some point anyway. So the dataset module also comes with many ways to quickly convert, NumPy data or HDF5, and it will return, it will take those as inputs and then return to you a tensor. So,
Mm-hmm. Cool.
and that was Bethany. She's another member of the data science group who missed our introductions. See some people taking advantage of the multitude of theta nodes. That's good. See a 128 node job for PyTorch Keras. You should feel free to return to the content from this morning if you had trouble running. We are online to help. Let's see. Let's go to theta and submit one of these. If I do theta, looks like it's set correctly. Okay, so I just do q sub. Okay. And why don't I go ahead and reshare, and I'm going to show, let's have a look at the PyTorch example. they're both similar in structure as far as the main is concerned. But now in the case of PyTorch, it's oriented more about creating a class that you can iterate over. So they have this torch utils data set class object that you should create a similar object that inherits from. And then the key pieces of this class are this get item and the length. And essentially what this means is TensorFlow, for its dataset object, needs to be able to tell how many objects there are in your dataset, so the total length. And in this case, it's just the length of the file list that we read in. And then the get item is it treats this like a list. So if it knows that this object has 100 items, it should be able to do item bracket 0 through 99 and get an input and a label back. And so that's what we do in this example here. We build this object. This is the method where I pass in the file list. It opens the file, reads in all the file lists, and then creates the object. We have a function for reading in the image. You can see where I also look for the XML file. I open the image using this pill library, the pillow library. And then we get our bounding boxes. And then we crop and resize the images. And then we return those images and the labels. And so in the workflow, oh, that's the other challenge. Okay. So I have these get data set function, which does that for both the training and validation. Where did I define that? It's in here somewhere. There it is. So this is just creating one of those dataset classes from the file list in the config file for training and validation, and it returns those. So you get those two. So now I have my data sets, but now I want a way of sampling those data sets to build batches. And that's where the Torch distributed sampler comes into play. The distributed sampler is your sampler for MPI, essentially. It takes the dataset objects as inputs. You tell it how many MPI ranks you're running with. What is the current rank? Should it shuffle at the epoch boundary? Should it drop any dangling, right? So you could have a batch at the end of your data set that's not an integer number that's equal to the batch size that you've requested, which I tend to just drop those. And then you have the data loader. So this handles the sampling. How do we sample the data set? And this is how do we load the data set. And the loading is where the parallelization comes in. So in a data loader, since we're using a sampler, we set the shuffle to false because the shuffle is going to happen in the sampler. I'm not quite sure why they require that, but that's just a key note. And then they also have a similar number of workers. How many loaders can you handle at the same time? And so that's where I use this config file to set. I set my batch size. I'm setting this persistent workers. That just means that when you when it's multi-threading these workers, instead of standing up a new thread for every image that it loads, it will have persistent threads. And that makes it easier for the profiling, because in the profiler, if you don't use persistent workers, for every image you get, you'll have an independent thread ID. And so it organizes all the threading based on those IDs. Anyway, it gets confusing. So now you have these loaders, and then you can iterate over the loader. So you could do 4 inputs labels in train loader, and that would return to you the proper inputs. I enumerate them here to get the batch number. So that's what it looks like in PyTorch. I ran the example on theta using this Q sub submit theta. And there's my job ID there. So I'm just going to open logdir job ID dot output and error, which is where the log file, the logging module puts your log output. So you can see the iteration, you can see the class labels, very similar to the TensorFlow. And then you get an images per second at the end. Does that help? And let us know if you have questions. I see people chatting in both channels. That's good. I see someone with the username DGUO on Theta GPU submitted a job to the full node queue instead of the training queue, which is why your job is not running yet. So you'll need to delete that job and then resubmit it with the proper queue name. Well, if there aren't any more questions, okay, well, I see is the Slack's being quiet. Um, there are people running on the systems in the reservations.
People can also ask Taylor all their hardest questions.
They can. It doesn't mean I'll be able to give them an answer. So tomorrow we have Deep Hyper demo and hands-on tomorrow from 10 to 12. And then we have profiling from 1 to 3. Profiling, we're going to be covering quite a few different methods. So that should be a busy session. And then on Thursday, we have the integration of inference into simulation, how to use your trained models in a traditional simulation setting on an HPC. And then Thursday from 1 to 2, we have a discussion of um, allocation programs, how to get allocations on our systems from Catherine. And we'll also have some time for follow-up, hands-on, lingering questions, issues. So I'm inclined to draw the Zoom portion to a close, but offer people to consider or continue debugging and asking questions via the Slack.